Welcome everyone. Today we'll guide you through the process of how we can integrate eBPF with Free5GC Core. More specifically, eBPF with UPF, which is a crucial component in data plane packet processing. In this demo, we will be setting up an end-to-end 5G deployment using eBPF-based Free5GC Core with OAI RAN. We'll be using software defined radio, that is in our case USRP B210, with our UE Nothing Phone 1. But before we dive into deployment, let's take a quick look at the architecture diagram to understand the components involved. So, as you can see, this is the architecture diagram of eBPF-based Free5GC Core. Here you can see all the components of 5G Core control plane that includes AMF, SMF, etc. AMF is connected to the OAI RAN, which is also connected to software defined radio, that is in our case USRP B210. And finally, the radio will be connected to our UE, that is Nothing Phone 1. Now let's dive into the architecture and workings of the eBPF based UPF, often referred to as eUPF. The eUPF plays a vital role in processing user plane packets, connecting the RAN and the data network through N3 and N6 interfaces, respectively. Starting from the kernel space, the N6 interface serves as the direct link to the data network. It acts as the entry point for the packet processing from the data network. When a packet arrives, it is first received by the NIC. From the NIC driver, the packet proceeds to the XTP hook points. At the XTP hook points, we attach eBPF programs. These eBPF programs operate in the generic mode of XTP. They play a crucial role in packet processing and manipulation. To manage these eBPF programs, we utilize user space eBPF programs and eBPF maps. These eBPF programs are designed to perform various tasks such as packet filtering and processing. They are responsible for directing the packets through the network stack and onwards to the application layer. We use eBPF maps to store essential information, including API addresses, interface names, and metric address, N3 and PFCP addresses, and the XTP mode as well. These maps serve as efficient data structures for communication between user space and kernel space. The library facilitates the reading and writing of data in the eBPF maps. It acts as a bridge between user space and the kernel space, ensuring seamless interaction with eBPF programs and maps. At the XTP hook, packets are subjected to filtering and processing through eBPF programs. Only packets meeting specific criteria proceed further into the kernel network stack. Packets that pass through the eBPF programs move into the remaining kernel network stack and eventually reach the application layer. In the context of 5G control plane, this typically means that they are directly connected to the SMF via the PFCP agent using the N4 interface. Additionally, API servers are integrated into the architecture to host Swagger APIs, accessible via web. These APIs provide a convenient interface for interacting with the configuration of eBPF programs, UPF pipeline, and XTP stats. To monitor the performance of the system, an inbuilt Prometheus server is incorporated. This server collects metrics and serves them to a Grafana dashboard for visualization and analysis. This HCOM eUPF repository, let's have a look at the eBPF programs that are attached to the XTP hook in Free5GC Core. These are the eBPF programs that are used in the Free5GC Core. Firstly, we have UPF program. This program is calling UPF pipeline eBPF program using that eBPF tail call function. Now let's have a look at N3 entry point. This program is the entry point for the data packets processed by the eBPF program through N3 interface. And similarly, we have N6 entry point that will act as an entry point for N6 interface. And nextly, we have N3 N6 entry point. All the implementation of eBPF program used for packet processing through N3 and N6 interface is done here. Now let's get started with the deployment process. First, you'll need to clone the HCOM Free5GC Compose repository onto your machine. This repository contains the eBPF-based Free5GC Core. Once you have cloned it, navigate to the repository. As we have already cloned the repo, let's get started with the commands. First is docker compose up. Now let's get started with the next command, docker ps. As you all can see, all the containers are up and running fine. Now let's get started with the AMF logs. Here are the AMF logs. As you can see, it is showing ng setup failure. That means G-Node B is not connected to the core right now. Now have a look at eUPF logs. So here are the logs of eUPF. As you can see, BPF arrays, map arrays, that is including API address, our PFCP address, and interface name along with metric address. That will be used to see the metrics of eBPF using Grafana and Prometheus dashboard. After that, we have the N3 address and XTP attach mode, that is generic. And nextly, we have the PFCP connection and handling of PFCP message using SMF. Now let's have a look at portal for Swagger. As you can see, this is the dashboard of Swagger API through which we can get configuration data of eBPF with UPF pipeline and XTP stats. Here is the configuration of our program, and you can see that there are interface names, that is ETH0 and ETH1. Here is the XTP attach mode that I have already mentioned earlier, that is generic, API address, PFCP address, PFCP node ID, and a metric address, and etc. Now let's move on to the UPF part. There are the components of UPF pipeline, that is UPF function, UPFR program, UPF QER program. Now let's have a look at our XTP stats. As you can see that it is passing all the messages from NIC to the user space, and there are no aborting, dropping or redirecting of messages.
So this is our 5G lab where we do all the testing, and here are some of our tools you can see. And this is the network diagram of the eBPF based Free5GC core, and on the server 2 here we are running the eBPF based Free5GC core, and this is a software defined radio that in our case is USRP B210, and this SDR is directly connected to the server 2 on which the eBPF based Free5GC core is running. Now let's have a look on our UE. So this is a UE, nothing phone 1, and you can see there are no network signals here. It means the UE is not connected to the RAN. And now let's try to run our OAI GNodeB, and let's see if we can have some changes in the USRP, because right now there is no light blinking here, but after running this command let's have a look on the USRP. So these are the logs from the GNodeB. You can see it is starting the USRP. USRP has been started. You can also see in this SDR the red and green lights are blinking, right? And now let's have a look on the AMF logs. And let's see if the N gap has been created or not. So you can see these are the logs of AMF, and now let's have a look on our UE. Let's try to connect it to our core. So putting it into airplane mode and removing it. Now you can see the 5G signal here, and let's try to run internet on the smartphone. Before that, let's have a look on the AMF logs. So these are the logs of our AMF. You can see the N gap has been established and the UE is connected to the core. Now let's try to run internet on our smartphone. So yeah, let's put it into maximum quality and moving on to advanced, setting it to 4K, right? So you can see our UE is connected and the 5G is running right now. And you can also have a look on the logs of eUPF. Let's move on to the terminal part.
Now, as you can see, the logs of eUPF and all the heartbeat responses. Now, let's have a look at the traces provided by the BPF programs. These are the traces that are provided by the BPF programs. Now you can also list out the eBPF programs, and you can see these are the C group programs, and we have the XTB eBPF programs like that UPF function, UPF FAR program, UPF QER program, and etc. These are attached to the kernel in XTP generic mode. Now you can have a look at the eBPF maps that include these things, that are basically programs array related to UPF pipeline, UPF existing stats, UPF route stats, and all.